given given a function f belonging to LP on the ball, then if we integrate over the ball f of x over absolute value of x, and this is in R2, dx, then we can decompose it with this Fubini type formula, which is actually the Courier formula or integration in polars, like this. Let's actually do it like this. So we're integrating over the line segment going from 0 to cosine of theta, sine of theta, like this, of f dz dh1 of theta, like this. So we have a function defined in a ball, and we can integrate along these rays like this, so long as we accept that we have this function 1 over mod x inside the integral of f. And this, I showed, just follows some change of variable formula. And you might be thinking, okay, but you told us that, and you guys already know, I'm sure, that LP functions are only defined almost everywhere. These are lines. How do we even know that they're defined there? Well, for arbitrary individual line, you don't. But we have lots of lines, right? We have this whole 0 to 2 pi amount of lines. So just as for a Fubini theorem, if you integrate a function, then you're integrating it amongst, you're integrating all these lines, then you're integrating let me just draw a picture. So using standard Fubini theorem, you're integrating like this, right? For almost every line along here. And it's not hard to see that for almost every line, you actually do have that the function will be well defined along here, if you consider the precise representative of the LP function. And the same is true here. So we can actually get away with this. And if you look back at the proof, all this is just using Fubini theorem in a different coordinate system. So, so if you believe that for Fubini theorem, then you should believe this. So for any arbitrary line, we don't necessarily know this is well defined, but for almost every one of these lines, these rays, it is well defined, and we can integrate it along the line and have this being true. Okay, so this is what we did last time, and we're going to use that now to try and give some key flavors of or some key points which indicate the flavor of Sobolev functions. So it's a whole subject, and I just want to tell you the main things and that I think you need to understand in order to have the background to understand the stuff we're about to do, and also the papers I want you to read and present on. So we're going to show the following. So suppose, again, we're doing everything in R2. So suppose we have a function u belonging to W1P of the ball like this. And u is scalar valued. Often u is vector valued, but in this case it's just taken to be scalar valued. Emphasize this by doing this. Then, and we want it to have 0 on the boundary. Then, if p is bigger than 2, we will show that the L infinity norm of this function is bounded by some absolute constant, the LP norm of the gradient, like this. And this will follow from our formula relatively easily, because what are we going to do? So, proof. So, consider the integral of the gradient. Let's write a gradient mod x over like this. Then we're going to apply Fubini, not Fubini, sorry, we're going to apply Euler's inequality. So then this is less than equal to integral of the gradient, power p, dx, 1 over p, and then integral of this thing, 1 over mod x, to the p prime, the Holder conjugate. I'll write down what this is in a second. 1 over p prime, just Holder's inequality, right? Where 1 over p plus 1 over p prime is equal to 1, which is equivalent to saying that p prime is equal to p over p minus 1. So p prime over p plus 1 equals p prime, and therefore 1 is equal to p prime of 1 over 1 minus p, which is equal to, p prime equals this, which is equal to p minus 1 p, and that gives the formula. All right, so key point to notice is that since p is bigger than 2, p prime is between 1 and 2, like this. It's not hard to see. Okay, so let's look at this term right here. So notice that if we do this integral, oops, minus 1, that's 1 over mod x, like this. Yeah, just breaking up the powers, and then we can apply our formula, right? So then this thing is equal to integral from 0 to 2 pi, integral from 0, which now I'm going to write it like this, cosine of theta, sine of theta, this, and now we're going to have just 1 over mod z, dz, let's write the h1 of z, h1 of theta. Let me try and separate off some things. Like this. Right? And this is the wrong exponent. This is 1 over mod z p prime minus 1. Yeah? And p prime is between 1 and 2, so p prime minus 1 is strictly less than 1. Yeah? So the integral from 0 to cosine of theta, sine of theta, 1 over mod z p prime minus 1, oops, dh1 of z is nothing but the integral from 0 to 1 of 1 over x p prime minus 1 dx, right? And as you know, this is now an integrable function, right? Improper integrals of type 2, you guys all do calculus, this thing is less than infinity because we have a root power of x. Yeah? And it's less than some particular constant. We don't actually care. Let's write down less than c. Well, it's actually equal to c for any x, equal to some constant c0, which just depends on the p. Yeah? So this inner integral here is just depending on this, or it's just equal to this, and we're integrating it for every angle. It's always the same thing. Yeah? So we actually have this. It's just 2 pi times this particular constant, c0. Yeah? Everybody happy? So this thing in the red box is just some universal constant just depending on p. Yeah. Cool. And this thing is what we have by hypothesis as something that is bounded. Yeah. So we have that this expression that we started with here will actually be bounded by just the LP norm of the gradient times some fixed constant. Yeah. So then we can apply our formula again. Integral around the ball like this. Let's write it like this. And now, again, by the formula, we're integrating from 0 to 2 pi, integrating from 0 to cos theta sine theta, like this. And now we just have du z, dh1 of z, and then d theta, and then all of this stuff is just bounded by, well, strictly speaking, 2 pi c0 times the LP norm of the gradient. Yeah. So at least half of these angles theta have to be such that that they are less than twice this, because if more than half were bigger than twice this, then we would get a contradiction. Yeah. Yeah. So in particular, there's lots of angles for which this thing, this integral here, is less than twice this. Are you all happy with that, or shall I give more details? Thumbs up if you're happy with that. All right, cool. So there exists theta 0 such that this thing, integral from 0 cosine of theta, sine of theta, du of z, dh1 of z, is less than 4 pi c0, the norm of this thing. Yeah, and then we can just use the fundamental theorem of calculus to. So let's suppose this is the angle theta 0. We can integrate from this point here up to the center. And because we've chosen the function to be 0 on the boundary, we have that u at the center, which I'm going to write u of 0, minus u of cosine of theta 0, sine of theta 0, absolute value, is less than this thing, right? 4 pi c0, like this. Like this, yeah? And then this thing is 0, so we actually have that this point here is 0, like this, okay? So we haven't shown the full thing, because what we've shown is just that the point on the center is actually bounded by some absolute constant times the norm, yeah? But all we needed to do to argue this for any other point was just consider this integral here, where x is replaced by whatever point we want, well, where 0 is replaced by whatever point we want. So if we pick some other point, say x0, like this, then every other step will still work. This thing will still be finite. We can still decompose, but then we'd have all the rays coming out like this. Yeah. So exactly the same argument will show that we can bound any other point inside the ball. And therefore our claim is shown. We have shown that if p is bigger than 2, then we actually have the function is bounded. Yes, it's essential. So at this point, if p wasn't bigger than 2, then p prime wouldn't be less than 2. And then when we do this thing, we'd have an integral where we don't necessarily have a root power of x in the one-dimensional integral here, right? So if we had 1 over x, then obviously it's not integrable, right? If we had 1 over x to the q, where q is bigger than 1, then it's also not integrable. Yeah? As you remember from calculus. That's right. That's right. But a Poincare inequality is not a pointwise inequality, right? A Poincare inequality is an integral inequality, which is something much weaker. Okay, the Poincare inequalities are not, are not known to everybody, so I don't want to get too deep into it. But yeah, but you know what I'm saying, right? That we're taking the integral of f minus its average and we're controlling it by the gradient. And indeed, we don't need p to be bigger than the dimension of the space, but it's a much weaker control. It's an integral control as a pointwise control. And this argument is not by any means optimal. It's just to give you a flavor. What we can do if we argue in a similar way, but are just more careful with our estimates, is we can show that not only is the function bounded if p is bigger than 2, it's actually Holder continuous. So we showed it's bounded with the assumption it's 0 on the boundary by controlling the difference between the boundary and the point, right? So morally, that's not a million miles away from showing some kind of Holder continuity, because we're controlling the difference between 2 points by the norm of the function. So this is an arbitrary dimension. So if u belongs to W1P and P is bigger than n, then u is Holder with exponent 1 over n over p. So does everybody know what Holder continuous means? Perhaps not. So i.e. u of x minus u of y is less than some constant times x minus y, the 1 minus n over p, and this constant c just depends on the norm of the LP norm of the function. Yeah, that's what we actually have, right? So we have pointwise control if we get p bigger than the dimension of the space. And as p gets bigger and bigger, then this n over p gets smaller and smaller, and this looks more and more like Lipschitz control, right? This is stronger as the p gets bigger. Yeah? Cool. So when you talk about Sobolev spaces, the more integrability you have of the derivative, the better off you are. And if you have p less than n, you do still have stuff, but you don't have pointwise stuff. You have integral stuff. So we have a Poincare inequality, which we'll get to later, but the first and simplest thing to say is that we have higher integrability of the actual function. So if p is between 1 and n, then u belongs to L p star, where p star, I think it's n minus p. Right, so as n gets close and close, as p gets close and closer to n, then we are more and more integrable, right? And so this integrability tends towards infinity. And as we just cross over this n and go to something bigger than n, then suddenly we are bounded, right? So this is sort of a continuous spectrum here. Yeah. Cool. So when we're dealing with Sobolev spaces, what you have to remember is that we're not going to do pointwise things with the derivative most of the time. For our purposes, we're just not going to do pointwise things with the derivative. We are going to integrate the derivative by parts. And if you look back at the past arguments that we did, that's what we use most of the time. Yeah? And you should also be aware that the more integrability we have of the derivative, the better control we have of the function. This stuff you can think of as a kind of inequality-based generalization of the fundamental theorem of calculus, right? So the fundamental theorem of calculus, you're controlling the function by integrating the derivative, yeah? But you have actually pointwise control. You can show that u of b minus u of a is the integral of the derivative from a to b. Yeah. If you abandon pointwise control and you're interested in inequalities and you want to do this for a more general situation, then this is the kind of stuff you get, and this is an incredibly important and useful theorem. On first sight, it can seem somewhat technical, and you might not see the value of it, but it is extremely useful. All right, so this is called the Sobolev inequality, and this is Murray's inequality right here, which is also considered part of Sobolev inequality, and that's the background we need on Sobolev functions. So several of you are quite familiar with this. Some of you are fairly new to this. Don't be too worried about it. I mean, these are like big chapters of PD books on this. We don't need that much about it. What we need is just the things I said. So, and you should also know that in the Sobolev norm, you can approximate any Sobolev function by a smooth function. So you can always have a smooth function if you want to, but you're going to have the same bounds on the integrability of the derivative because you're approximating in the Sobolev norm. One of the most useful things we have with respect to Sobolev space is we get compactness in a certain sense, in a sense of weak convergence. So let's talk about weak convergence. In LP. I'll just write LP. So given a sequence of functions fk belonging to LP, we say fk converges weakly to f belong to LP. So let's give us. We're going to do this. We're going to do everything on bounded domains. So let's just give ourselves a domain U. If and only if the limit as k tends to infinity of the integral of U of fk times g is equal to the integral of f times g for all g belonging to L p prime of U. So by Holder, the largest class of functions we can test our fk with are functions in LP prime, right? Because we have that fk g is less than flp fk lp g lp prime, right? So we don't know that this expression is bounded unless g is an LP prime, right? So this is the largest class of functions we can potentially write this product, right, as an integral function. Yeah. So what it's saying is that for this largest class of functions, if we consider this integral, then we want this thing to converge to this thing, okay? And this is convergence in averages. So this implies, and it also is implied by, so given any measurable set, so sets are always measurable, so I'm just going to say, no, sets are not always measurable, but for us, sets are always measurable. So given any set, in other words, I'm only going to consider sets that are measurable. Then let's call this thing star. Star implies that the integral of E of f(x) dx tends to the integral of E f of x dx. So sometimes this is called, or it's considered as integral as convergence in averages. So we're not interested in pointwise convergence. We're not interested in norm convergence. We're not interested that the LP distance between Fk and F tends down to 0. We are interested in this kind of convergence in averages, right? Which is a much weaker notion of convergence than LP convergence or pointwise convergence. Yeah, so it is a much weaker notion of convergence. But what is good about this is that often we can find subsequences that converge weakly, whereas showing that something converges strongly in LP norm can be quite difficult. You need to have quite strong hypotheses a priori for this to happen. But under relatively mild hypotheses, we can actually have that can actually abstract a subsequence that converges weakly to some limiting function f, and this function f is uniquely defined by this. And this implication is kind of trivial. We just test this against the characteristic function of E. The characteristic function of E will always be in LP prime. Yeah? Yeah, but the whole thing is bounded. So I said U is a bounded set, but maybe I emphasize this. Take U to be bounded. So some of you have seen weak convergence of measures, right? You're quite comfortable with weak convergence of measures. You know, this is a very similar notion, right? Weak convergence of measures is when we test against C1 functions, sorry, C0 functions. Yeah? So we say actually maybe this isn't a helpful thing because many of you haven't seen measures UK converge weakly. So this is something you use a lot in probability and of course in measure theory. Zero U, right? This is weak convergence of measures. And this notion is very similar. Okay. All right, so as promised, what's good about this is that we can actually find things that weakly converge. So theorem. Suppose Fk belongs to LP of U. P is between 1 and infinity. Then, and that's uniformly bounded, so the supremum of K of the LP norm is less than infinity. Then there exists a subsequence Fkn following to Fkn such that Fkn converges weakly to NLP to F. So it's a relatively mild condition to just have that the norm is bounded, right? But from this, we can extract a subsequence that converges weakly to some limit, right? And of course, that's absolutely not true if we consider strong convergence in LP, right? That's absolutely false. Yeah. So this is one of the theorems we're going to use, and this is a consequence of some function analysis theorem, the Banach-Alug theorem, about compactness of the dual of the unit ball. But we're not gonna go into the details of how this works, but this follows from function analysis principles. You can also prove it in a more elementary way. And the second theorem we're going to use is Rellich compactness theorem. And I don't know how to spell, so I'm going to write compactness theorem. There. So suppose we have a sequence fk. Now let's use different things. Let's call them uk belong to w1 p of u, and uniformly bounded. Then there exists a subsequence ukn such that, so uniformly bounded means uniformly bounded in the norm, in the Sobolev norm. I should emphasize that. W1P. In fact, it's enough just to have that the gradients are bounded in LP. Then there exists a subsequence such that UK converges strongly in LQ. We've used U twice, let's use omega. For any Q, so I'm taking everything to be bounded, less than the Sobolev exponent like this, where again, did I still have it? I don't, so where P star is equal to NP over n minus p, like this. Okay, so this is only new and interesting if p is between 1 and n, because if p is bigger than n, as we've already learned, these guys are Holder continuous, so it's just a Zollier scalar theorem, right? Yeah, because they're uniformly Holder continuous, therefore they're equicontinuous. Yeah. But if p is between 1 and n, then we don't have that kind of control at all. But nevertheless, we have that the subsequence will converge strongly for every q between 1 and p prime, where p prime is the Holder exponent. So just from this hypothesis, we know that it is integrable up to p. If we have something a little bit less, we have that it's going to converge strongly in the LQ norm. Okay, so this is quite a far. Go ahead. I can include what? Oh yeah, I can include, yeah, that's true. That's true. I can include q equals 1, yes. Yeah. In fact, since everything is bounded, we have that the higher LP norms control the lower ones, right? Just by Holder's inequality. So yeah, it's stronger as we let q tends towards p prime. Okay, so this is quite a far-reaching generalization of a Scalia-Zähler, because the hypotheses are much weaker, right? We have a much weaker hypothesis than having equicontinuity. We just have that this is a Sobolev function whose Sobolev norm is uniformly bounded. And then from that, we extract that the actual function converges strongly. Yeah? And in fact, it is proved by convolving the function and then applying a Zollier scalar. So it's not a million miles away, but it's nevertheless very useful and very much stronger. So notation. if UK belongs to LP, converges weakly, to U, we write like this, so UK, and we write half of an arrow. So this half arrow means weak convergence to U, and either we write whatever the space is. So I tend to write it on top, that like this. That's how we denote weak convergence. And if there's a full arrow, then that's strong convergence. And if, let's say, WK belongs to W1P, and then WK converges weakly to W in this space, means that the gradients converge weakly. So the gradients WK converge weakly in LP, the gradient, and the functions actually converge strongly. And WK. So when a strong convergence is a full arrow, and then we write Q, where Q is less than the Sobolev exponent of P, like this. Okay, so why this definition of weak convergence? Well, just because the gradients will form a bounded sequence in LP, we know we can extract something that will converge weakly, and we also know by Rellich's theorem that passing to another subsequence, we can expect it to converge strongly, right? So that's why, for free, we just extract the sequence that does both those things. In fact, this thing does imply this thing by not too hard arguments, but let's not go into it. So this is what we mean by weak convergence in Sobolev space. We mean that the gradients converge weakly, and then for free we get actually that the functions will therefore converge strongly in LQ for Q less than the Sobolev exponent. Okay. Question. Suppose we have a sequence. Well, first let's take a set K, which is contained within 2 by 2 matrices, and a sequence UK from inside Sobolev space W1P omega, which is in R2 into R2, and we have that UK tends weakly in W1P to some limiting function U, and we have that the integral around omega of the pth distance of the gradient away from K dx tends to 0. Does this imply that gradient of U belongs to K almost everywhere? Okay, so if we had strong convergence, then this would be true. Yeah? But we don't. We have weak convergence. So our question is, does weak convergence allow this to be true? Can we show that the limiting function, oops, this is the sequence, UK, like this. The limiting function is forced to be inside this set K. So we have let's write our set K just like as a circle, because we're considering stuff like this before. So if we have that for our sequence, the gradients are closer and closer to this particular set, does it imply that the limiting function is such that this guy has to be inside the set K? Okay. Now, in the case where K is just the rotation matrices, this is true. This is true by Friesecker-Moller-James theorem, right? Because if the gradients are closer and closer to this actual set of matrices given by the rotations, then we know that it's quantitatively with the same control close to a fixed rotation. Yeah? So it's closer, so these functions are actually such that they're close and closer to a fixed rotation. We passed the limit, that limit function will just be an affine function taking its gradient in one fixed rotation. Yeah? So in the special case when we take K to be the set of rotations, then it's definitely true. Do you see what I mean? Yeah, so by Friesecker-Moller-James, Friesecker-James-Miller, true if K is just the rotation matrices. In fact, it's rather a weak conclusion from Friesecker-James-Miller theorem. Yeah? We're asking in more general contexts. And more general context, the answer is no. In general. So, suppose there exists A comma B inside K, for which the line segment joining A to B is not strictly contained within K. Okay, and the rank of A minus B is equal to 1. Then there exists some V, let's take it to be minus 1, such that A of V equals B of V, right? So if the rank of A minus B equals 1, it's a rank 1 matrix, right? So there exists some, so the kernel is non-trivial, so we can just pick some V inside the kernel of unit length, such that this is true. Yeah? Okay, so here's my claim. We can define how should I express this? So claim let V perp be the orthogonal vector to B, or be one of them. 0, and let's write H plus to be the set of all x belonging to R2 such that x dot V perp is bigger than or equal to 0 and H minus be the set of all x belonging to R2 such that x dot V perp is less than 0. So we're taking V, this is direction V, this is V perp. So H plus is this side, this half space, this is H minus, like this, yeah? And then define u of x to be equal to, let's start by saying this, yeah, u of x equals this, is equal to A of x. So this is A is just a 2 by 2 matrix, so we just activate with this vector x if x belongs to H plus, and B of x if x belongs to H minus. Okay? So this is a well-defined function, right? Except what? Except that on H plus, which is this line here, is defined by A of x, on H minus, it's by B of x. It's B of x, right? So we claim that it's still nevertheless continuous. Then U is continuous. U is continuous. All right. And the reason it's continuous is because these matrices A and B agree along the direction V, right? So if we are right here on the line which separates the half spaces, then our function is U of A, but if we move down a little bit, it's equal to B of x, but we are so close to being in the direction V that as we get closer and closer from this side to this point, then we will actually agree. We'll actually agree this way. Yeah? So this thing is continuous just from this condition. And if we didn't have this condition, then this would not be continuous. Do you see what I mean? Yeah? So this is a well-defined continuous function. Actually, its gradient is just A and B, so it's even Lipschitz. It's even Lipschitz because the gradient is bounded. And we can repeat this construction. So I'm running out of time. If you have to leave, just leave. But let me just finish this little moment. So we have a function which is like this. It's A here and it's B here, and the gradient jumps across this interface. We could actually do it the other way around, where it was B here and A here. Exactly the same argument would work. So if we take a square like this, where this is direction V and this is direction V perp, then for any number of strips we want, we can cut it up into strips like this, and then we can layer in gradients A, B, A, B, A, B. Yeah? Then the gradient of, let's call this thing, let's cut these up so that these are like length 1 over k. So UK is defined by this. Then gradient of UK just belongs to AB almost everywhere. Yeah? Cool. And if A and B are inside our set, so the UK belongs to K almost everywhere. Oh. Okay, so for Wednesday, what I want you to do is to think about the limit of this function that I've defined here. Tell me what this limit is. So it's got a weak limit. We know this, right? And then tell me what the weak limit is. And then from that understanding, tell me why, if we don't have the entire line segment AB is contained within K, then it's not necessarily the case that the limiting function U is such that the gradient belongs to K. That's what I want you to think about for Wednesday. So play over this example, think about it, and then tell me why. Tell me firstly in this particular example, tell me what the gradient of the limiting function U is like, and then use that to answer this question. All right, great. So I'll see you all on Wednesday. Have a great day. Bye-bye, people.